Los estudiantes, espero que todos se encuentren muy bien. Bienvenidos a la cuarta semana del curso. Vamos a discutir un poquito lo que tenemos para el módulo 4. Me disculpo, ¿verdad?, por no estar presente el jueves pasado, debido a que, de nuevo, donde estoy viviendo hay muchas interrupciones de energía eléctrica. Están bregando con eso. Gracias a Dios, los de Luma, dentro de todo, han sido un poco diligentes en esa parte. Vivo en un área que es un campo, ¿verdad? Y debido a donde está la infraestructura es un poco de difícil acceso, pues han tenido un poco de retraso. Pero nada, trabajamos con lo que tenemos. Para el módulo 4 vamos a estar trabajando con el tema de los protocolos de enrutamiento. Recuerden que los protocolos básicamente es lo que establecen las reglas de las comunicaciones, ¿ok? Por ejemplo, el protocolo de HTTPS que ustedes están viendo aquí en la barra de direcciones, es un protocolo que lo que nos permite es la comunicación en la web, pero el AS incluye lo que es la parte de seguridad aplicando lo que es el TLS, Transport Layer Security, o incluye también lo que es el Secure Sockets Layer con el IPsec. La realidad es que, de nuevo, todos estos mecanismos de seguridad lo que tratan de disminuir es la superficie de ataque, no son infalibles. Los hackers hoy día pues, también saben cómo corromper estos mecanismos de seguridad, saben cómo hacer un bypass a un factor multiautenticación, en fin, nada de los mecanismos de seguridad son infalibles. ¿Qué es lo que nosotros tratamos de siempre hacer desde el punto de vista de la seguridad? Siempre, ¿verdad?, llevarlo a un nivel de riesgo aceptable. Bien. Vamos entonces a hablar un poquito del módulo 4. Para el módulo 4, antes de todo, ¿verdad?, tenemos dos actividades, que es básicamente la instalación de un router empresarial y la parte de herramientas de diagnóstico de Cisco. Para cada uno de estos laboratorios yo le puse un video tutorial que básicamente son videos en YouTube que ya personas que han tenido la experiencia con estos laboratorios, que los han podido montar, obtener una puntuación perfecta. Por lo tanto, mi recomendación es que siempre vean estos videos primeros, obviamente, para que se puedan familiarizar con la plataforma, familiarizar con lo que hay que hacer y que ustedes entiendan, porque, de nuevo, a mí no me molesta que saquen 100 en todos los laboratorios y que saquen 100 en la clase. Es más, para mí eso es formidable. Lo que quiero es que vean con estos videos es la dinámica que tienen que seguir para estas simulaciones y por qué esos laboratorios son importantes. Porque, por ejemplo, cuando hablamos de un router empresarial no es un router igual al que tenemos en el hogar. Router sigue siendo un router, no importa si es para un SOHO, que es un Smart Office Home Office Network, o si es un router a nivel empresarial. Lo que cambian son sus capacidades, pero el router en sí es un dispositivo de la capa 3 del modelo OSI, que es un dispositivo que me permite trabajar con segmentos de redes y tiene varios algoritmos para seleccionar la ruta con el menor tráfico, menor congestión, más corta, entre otras cosas. El router trabaja más a nivel de IP address, que es la dirección lógica que identifica el equipo conectado en la red. Bien, comenzamos un poquito. Vamos a hablar, ¿verdad? Para efectos de este curso, yo siempre les recomiendo que veamos los videos del profesor Messer. Gente, saquen tiempo, véanlo. Para mí, mi experiencia es el mejor recurso que existe para que ustedes puedan aprobar estos exámenes de Network Plus sin ningún problema, ¿ok? profesormesser.com, como les he explicado en las conferencias anteriores, para efectos de este curso, estamos alineados a lo que es el Network Plus, la versión 009, que es una de las más recientes, y entonces una vez entremos aquí, ¿verdad?, le damos un clic a este banner y vamos a buscar, ¿verdad?, la parte que nos corresponde, que es la parte de los protocolos, ¿verdad? Estamos ahora mismo en los fundamentos de protocolos de enrutamiento. De nuevo, ahí tenemos las topologías, direccionamiento IPv4, ambientes de redes, tecnologías de enrutamiento, ¿ok? Tecnologías de switching, dispositivos inalámbricos, instalaciones físicas. Miren todo lo que hay. O sea, la realidad es que hay un montón de recursos, ¿ok? Esto, básicamente, lo que es el troubleshooting, todo esto es básicamente para trabajar el último módulo. Ya la parte 5 sería para el último módulo. Básicamente, yo para esta unidad, yo trabajaría, ¿verdad?, el tema, ¿verdad?, de protocolos de enrutamiento. Vamos a ver si los encontramos por aquí. Ok, routing technologies. Bueno, tendríamos que trabajar con todos estos tipos de enrutamiento para que ustedes entiendan, ¿ok? Vamos a ver estos videos brevemente y retomamos, ¿verdad?, la conferencia.
The routers that we use in our homes and our offices have an important job of forwarding traffic between one IP subnet and another. It's a relatively straightforward process, although there is a lot of technology under the surface that makes this happen. But if we were to look at this in a very simplified form, we could see that the router is performing a series of relatively simple steps. The first step is to identify what the destination IP address might be for incoming traffic into the router. It looks into the packet, identifies what the destination IP address is, and makes a note of where it should be sending this traffic. The router then examines some tables to determine what the best route will be for this particular packet. If the destination IP address of this particular packet is associated with a subnet that is directly connected to this router, then the router simply sends the packet onto that local subnet. But in many cases, the destination IP address is on a subnet that is not locally connected to this router. The router will examine that routing table, determine what the best next hop might be, and then send the traffic out that particular interface. This next hop is the IP address of the next router down the line. And when that router receives this packet, it performs the same process again until the packet finally makes its way to its final destination. As you can imagine, that routing table becomes very important. And when we're troubleshooting routers, we refer often to the routing table, what the next hop might be, and determining where these packets should be going once they leave our router. If a router refers to its table and does not find a next hop for that destination IP address, it will simply discard that traffic. So you can see why having a valid routing table becomes very important. Let's look at this network diagram. There are 3 separate routers in this network diagram and 3 individuals that would like to communicate with each other. In this case, let's focus on router 1. You can see router 1 is connected to 3 different subnets. We have a subnet 10.10.10.0/24. There's another subnet between router 1 and router 2 that is the 10.10.40 network. And then another subnet between router 1 and router 3. That's the 10.10.50 subnet. Those 3 subnets are directly connected to router 1. So if we were to look at the routing table for router 1, it would see the route for 10.10.10.0/24, 10.10.40.0/24, and 10.10.50.0/24, and all of those networks are locally connected to this router. The problem occurs if Sam would like to communicate to Jack. Although router 1 knows about the local networks, it has no idea that there are more networks on the other side of router 2 and of router 3. And those particular networks of 10.10.20.0/24 and 10.10.30.0/24 are nowhere in this routing table. This means if Sam wants to send traffic to Jack, Sam will put this packet out on the network. It gets to router 1. Router 1 examines the destination IP address of 10.10.20.2 and then looks through its table and realizes there is no 10.10.20 network in the routing table, and the packet is discarded and never makes its way down the network. One way that we could create a more complete routing table is to build it ourselves. This administrative creation of a routing table is referred to as static routing. And if you would like to build static routes as the administrator of your routers, then you will manually be configuring these routes inside of every router that you use. Static routing is a very quick way to configure a route inside of the router. And if you're managing a smaller network, this might be a perfectly reasonable way to manage where the routes might be. Because we're static routing, there's no overhead that you would normally see from a dynamic routing protocol. We'll talk about dynamic routing in a future video. So there's no CPU cycles, there's no memory usage. We are simply adding the route ourselves, and we don't have to do any additional processing to the routing table from there. This is very common for remote locations where you might have a single internet connection into that remote site, and all communication takes place over that single connection. We often refer to these as stub networks. And because we don't have to worry about any type of dynamic routing updates or having any changes to the router configuration because of those updates, this is a relatively secure form of routing. However, this can be challenging to configure on larger networks. Configuring a handful of routers with their own static routes is relatively straightforward. But if you're managing hundreds or thousands of routers, manually configuring a static route in each of those routers could take quite a bit of time. This also relies on you adding the correct routes to every router. There have been times when I've configured static routes and I've set up my own routing loop within my network because of a misconfiguration. And as the name implies, these routes are static. They don't change once you've configured them. So if there are changes to your network, you'll need to manually log into your routers and make those configuration updates to the routing table that match the changes to your network. This also means that there is no automatic rerouting if something happens on your network. You will need to manually configure these routes if anything needs to be routed in a different direction. So let's configure some static routes for router 1. We know that we have our 3 locally connected routes, but we also have these additional 2 routes, one that's behind router 2 and one that's behind router 3. This would be the 10.10.20 network and the 10.10.30 network. So we might SSH into router 1, and at the command line, we would begin to add additional static routes. For example, we might tell router 1 that if it receives any packet coming through with a destination IP address that matches the range of 10.10.20.0/24, then send that particular packet to 10.10.40.2. So if the packet does come through with that destination that needs to go to the local network that Jack is connected to, it will send all of that traffic to the IP address 10.10.40.2, which is located on router 2. At that point, router 2 will examine its own routing table and know that the 10.10.20 network is locally connected and send that packet on its way. We can do the same thing with the 10.10.30.0 network. So we will manually configure a static route that if any destination traffic is going to 10.10.30.0/24, then send all of that traffic to 10.10.50.2, which means all of that traffic will go to router 3. Now that we've configured those static routes in router 1, anytime those additional networks are seen as a destination IP address, router 1 will know exactly where to send that traffic.
Ok, mi gente, ahí vimos un poquito del enrutamiento estático. Es un poquito confuso, ok, desde ahora les digo, es todo lo que tiene que ver con routing, enrutamiento estático, enrutamiento dinámico, son un poquito confusos, pero de nuevo, véanlos con calma, recuerden que esto está en la web, saquen un poco de tiempo, gente, entender redes no es tan fácil como se pinta. Muchas personas a veces piensan, ¿verdad? A veces tenemos una misconcepción de de las personas que estudiamos sistemas de información, ciberseguridad. Son carreras fáciles, son carreras que es estar sentado detrás de la computadora. Mire, no, esto es, a veces la complejidad de esto es casi similar que una profesión de ingeniería, casi, de hecho. Muchas de las personas que estudian este tipo de carreras muchas veces trabajan directamente con los ingenieros y pueden ser profesiones como ingenieros de redes, o sea, que ustedes vislúmbrense mucho más allá. Estudien, practiquen, hagan estos laboratorios, lean y trasteen. Miente, en este campo no se puede ser tímido, hay que ser presentado, hay que experimentar, hay que dañar, volver a reconfigurar y seguir. ¿Ok? Seguimos por este otro video.
Static routing requires the network administrator manually configure every route on every router in the organization. If you have 3 or 4 routers, that might not be a big problem. But if you have tens or even hundreds of routers, you might want to have a more automated way for configuring your routing tables. One way to do that is through the process of dynamic routing. Dynamic routing will have the routers handle this process for you, automatically discover these routes, and update each other as to where the best route might be. This means that you, as the network administrator, don't have to do any type of static route configuration. You don't have to SSH into the router, make any configuration changes, or update those routes if anything changes with your network infrastructure. Anytime you bring a new router online, all of the other routers will automatically know where the new route is. And if you happen to remove a router from the network, all of the routers also know that that route is now no longer available. There is a bit of overhead required inside of the router to be able to automatically discover these routes and update the routing tables. This will require some CPU and memory inside of the router, so you may need to do additional monitoring to make sure that your router is able to handle that load. This also requires you to initially configure the dynamic routing protocol. This may be a relatively easy configuration process, or it may require additional planning and engineering to be able to implement it properly in the config of the router. Let's look at this network configuration where we have Sam that may want to communicate across the network to Jack or to Tilk. You'll notice that there are 3 different routers. And for this particular example, let's focus on router 1. You'll notice that router 1 is directly connected to 3 different subnets, but there are 2 subnets on the other side of router 2 and router 3 that router 1 simply can't see. So we need some way to update router 1 with those additional routes. One way to do this would be to have router 2 send a routing update via EIGRP to router 1. Router 1 receives that update and then updates its own routing table with this new route to 10.10.20.0/24. And the way that you get to that network is to go to 10.10.40.2. We also have another EIGRP update that has come from router 3. And when that update is received, router 1 identifies a new route to 10.10.30.0. That's the subnet down at the bottom. And you can see that the next hop is 10.10.50.2. All of these updates occurred in real time behind the scenes without any type of user intervention. And if we happen to add or remove routers from this network, this routing table will be updated with an additional EIGRP update that will either add or remove those routes from the table. Although it looks relatively straightforward to perform these dynamic routing updates, there's actually a lot of work that occurs behind the scenes. First, the router needs to listen to the traffic that is on the local subnet and see if there are other routers that are sending routing updates that it can use to build its own routing table. These are very often sent directly from router to router, either directly or with a multicast. Once a router then builds its routing table, it needs to inform other routers of routes that it knows. So it will send its own multicast to other routers that are nearby, informing them of all of the routes that that router happens to know. Once the other routers receive this update, they need to interpret this information and determine if that's a better route than what they already have, or if they should use this as a secondary route. Different routing tables use different methods to make these decisions, and they will update their routing tables differently depending on the protocol you happen to be using. And of course, if there is any change to the network infrastructure, these routers need to inform all of the other routers that the change has occurred. So if we add a new link into a router, we remove a router, or we add a router, we need to make sure that all of our routing tables are updated across the entire network. There are a number of different dynamic routing protocols to choose from. So which one would be the best for your particular implementation? Different routing protocols make routing decisions in different ways. For example, would you like your traffic to be routed based on the state of the link, whether the link is up or down? Or would you like to be able to make that decision based on the number of hops that a link might be away from you, or the speed of that connection? Based on the routing protocol that you're using, that decision might be very different. Some routing protocols will use a different criteria to determine the best way to get to a remote location. You might also find that some routing protocols are able to make changes very quickly if anything happens to the underlying infrastructure. So if you add a new router to the network, it might take a number of seconds, or it might take a minute, depending on the type of dynamic routing protocol that you're using. And in some cases, we need to take into account the type of router that we're using. Some routing protocols, such as BGP and OSPF, are very common and can be used across many manufacturers' devices. Some routing protocols, such as EIGRP, may work best in a Cisco-centric environment. So if you have a lot of Cisco routers, that might be a better routing protocol for you. Although EIGRP tends to be very Cisco-centric, you may find EIGRP is also available on other manufacturers' routers. But there are some aspects of EIGRP that are proprietary to Cisco, so you tend to see it mostly in Cisco-related configurations. But one advantage of EIGRP is that it is relatively easy to set up. You would turn on EIGRP in your Cisco router, give it a few minor configuration options, and it's now up and running with the EIGRP protocol. When there are changes, EIGRP tends to converge relatively quickly, and it's also able to identify any loops and prevent those from occurring on your routed network. EIGRP is also very good at identifying other EIGRP-enabled routers and sending updates over a minimum of network traffic. This keeps your network more efficient and leaves your bandwidth available for other applications. If you want a more generic dynamic routing protocol that can be used across different manufacturers' routers, then you might want to try OSPF. This is the open shortest path first routing protocol, and it's one that you'll find available on a number of different manufacturers' devices. This is often implemented in a network where you have complete control of those systems. We often refer to this as an AS, or an autonomous system. For example, if you're running a wide area network that has 50 different routers, those 50 routers would be part of your single autonomous system. Another advantage of OSPF is that it's available on many different manufacturers' devices. This is a common standard, and you can download this standard from the internet and read through every aspect of OSPF. We refer to OSPF as a link state protocol, which means it determines what the best route is based on uptime and availability between the different OSPF routers. OSPFs can be used to assign costs to an individual link, so certain links may have a higher cost than another. This allows OSPF to make routing decisions based on what the least cost might be. This cost is often associated with how much throughput may be available on a particular link, if that link is up or down, and how long it takes to traverse that particular connection. With OSPF, the lowest cost and the fastest path is going to be the best route to a remote location. And if there are identical costs on OSPF, many implementations will allow you to load balance across both of those links. If you need to route traffic outside of your autonomous system to other organizations, then you might want to use an external gateway protocol such as BGP. BGP is the Border Gateway Protocol, and it's commonly used on our wide area networks and internet connections. Connecting the internet together and being able to dynamically update the routes on the entire internet is a daunting task. And this particular routing protocol was designed with this specific task in mind. Sometimes you'll hear BGP referred to as the 3 napkins protocol because it was sketched out on napkins initially to solve this particular type of problem. If your organization has one or more connections to the internet and you want to be able to dynamically route to those internet sites, then you'll want to use a protocol such as BGP.
Bien, ya vimos un poquito de esos protocolos de enrutamiento estático y dinámico para efectos de la certificación, ¿verdad? No es que vengan miles de preguntas, pero siempre tienen que estar aware. Recuerden que lo más difícil de networking es el routing. Las tecnologías de enrutamiento es lo más difícil que hay en redes. No hay nada más difícil que el routing, mi gente. Está switching, pasa que switching es a nivel de capa 2 del modelo OSI, y recuerden que los switches trabajan más con las direcciones físicas de la computadora. ¿Cuáles son las direcciones físicas de la computadora? Lo que es el MAC address. Pero ya a nivel de capa 3 del modelo OSI entra lo que es el routing. Routing, ahí entran los routers Small Office, Home Office, pero también entran los routers corporativos. Y la realidad es que, de nuevo, la Internet que ustedes conocen hoy día, que es la red más grande a nivel mundial, que se clasifica como un Wide Area Network, existe gracias a varios routers que están interconectados entre sí. ¿Ok? Seguimos con los videos, ya lo que nos quedaría es uno o dos más y seguimos adelante con la explicación de las tareas.
The job of a router is to evaluate incoming traffic, determine what the destination might be for that traffic, and then send it out the appropriate interface. The router is effectively determining what direction a packet might go to depending on the knowledge it has about the rest of the network. To be able to make this decision about where traffic goes, we need a routing table. And fortunately, most devices have a routing table. The workstation that you're using has a routing table. The servers that you're accessing have routing tables. And of course, the routers themselves maintain their own routing tables as well. For the router to be able to make the right decision on what the best route would be to a destination, it refers to this routing table. So everything that we do when we're troubleshooting a router will begin and end with the information contained within that routing table. One thing you might even find with a router is that there may be multiple ways to get to a location, and there will be a tie as to which route a router might choose. Fortunately, there are ways to break the tie within the router. And in this video, we'll look at a number of ways that tie breaking process might occur. Let's look at a routing table. This is a routing table I pulled from a Cisco router, but it's almost identical in form and function to routing tables that you would find in a workstation, in a server, or in any other manufacturer's router. In this particular example, this routing table was built based on a number of networks that were directly connected and routes that were received using the RIP dynamic routing protocol, specifically RIP version 2. If we look at the routing table, the top part of this routing table is a legend that gives us more information about the codes that are used within the routing table itself. In the bottom is the routing table, and you can see that the first set of letters on each one of these lines corresponds back to a different set of codes that are shown in that legend. For example, you can see the first line of this routing table starts with the letter C, which means that that particular route is directly connected to this router. If we want to see the route that was added using RIP version 2, then we need to find a line that starts with an R. And indeed, there is a line that has an R, which means that everything on this line was created because of information that was received by this router using the RIP version 2 dynamic routing protocol. And you can see there is a lot of information contained within this line. We can make out some IP addresses. There are different values such as 120/1, and it does appear there are even counters here along with information about specific interfaces. Let's break out just this line of information to determine what is contained within this line of a routing table. Let's break out this line of information to see which each one of these provides. We know that that first R at the beginning of the line is the route code. And if we refer back to the R in the list of codes, it does say that this was received using the RIP protocol. The next one is 10.10.30.0/24. This is the destination subnet that has been added into the routing table along with a prefix length of /24. We also have the 120/1. This is actually two different values. The 120 is an administrative distance. We'll learn more about administrative distance in a moment. And the next is a metric. We'll also talk about metrics in this video. You can also see that it's via 10.10.50.2. This would be the next hop or the destination that we would be sending this traffic if we needed to go to this particular location. We also have this time value. This is a timestamp that tells us how long this route has been active inside of this routing table. And in this case, this route has only been active for 14 seconds. And lastly, you can see the outgoing interface that would be used. Sometimes this interface is included. Sometimes it's optional, depending on the routing protocol or the router that you're using. But it's sometimes nice to see that this particular next hop is one that we would reach by going out a specific physical interface in that router. So when the router is making its routing decision on where traffic should go, it's evaluating everything in this routing table to determine if this would be the best possible route to use to forward this traffic along to the next hop. One of the first things that a router is going to evaluate is where this particular traffic is destined. We need to be able to look at the destination IP address and compare that to the subnet IDs and prefix links that are contained within the routing table. If there's a match, then we'll know where to forward this traffic. This means that this IP address range and prefix length becomes an important consideration when we begin to forward traffic. We need to look at both of those together to determine if this is the best possible route for this traffic. And if you were to look at a routing table, you may find that there are multiple routes listed to a particular subnet, but there might be different prefix lengths in each one of those lines. So you might need to evaluate each individual line of a routing table to determine which one is the most specific for this particular route. For example, let's say that you need to communicate with a device that's located at 192.168.1.6. And your routing table has three different routes that would match that particular IP address. One of them is 192.168.0.0/16. The other is 192.168.1.0/24. And the third is 192.168.1.6/32. All of these would be valid routes to that particular destination, but only one is the most specific. We need to evaluate not just the subnet ID, but also the prefix link to determine which one of these is the most specific for that particular destination. And if we were to look at 192.168.1.6, we would know that 192.168.1.6/32 would be the most specific route. In fact, that is the most specific route because a /32 is specific to an individual IP address, in this case, 192.168.1.6. Now, if this route was not in our routing table, we would have to choose between 192.168.0.0/16 and 192.168.1.0/24. The /24 is the more specific route than the /16, so we would choose the middle route if we had a choice between those two locations. This can get even more complicated if your routing table happens to have identical routes to a location that go to different next hops. How do you know which next hop would be the correct one if everything else was identical? And the one way that you would be able to make that determination is by examining the administrative distance. Different routing protocols are assigned different administrative distances within the router itself. This allows the router to pick the best route based on the type of protocols or the type of information that it has received. For example, if this is a local connection, it is physically connected to the router, this is the best possible way to get to that subnet. So it has an administrative distance of 0. As you can see here, the lower the administrative distance, the better the route might be. If you have manually configured a static route, the router assumes that you must be the most knowledgeable person for that particular route, so static routes have an administrative distance of 1. If this route was added to the routing table using EIGRP, the administrative distance is 90, and if you receive this route via OSPF, the administrative distance is 110. You can see that other dynamic routing protocols and methods are listed in this table with the appropriate administrative distance for a Cisco router. In some cases, the routing protocol itself may be in a position where there might be duplicate routes to a particular location, and the routing protocol has to make a decision on where the best route might be. In that case, we will want to look at the routing metric to be able to break that tie. Routing metrics are an internal value that are used by the routing protocol itself. So BGP has its own set of routing metrics. OSPF has a completely different set of routing metrics, and EIGRP uses its own set of routing metrics as well. This means that you can't compare routing metrics across different routing protocols. The routing metrics used for BGP are very different than the routing metrics used for EIGRP, and there's no way to compare or contrast those routing metrics across routing protocols. But similar to an administrative distance, BGP might create its own set of routing metrics to a particular site, and then it can determine what the best route might be based on its own internal set of routing metrics. For example, the routing metrics for BGP might be 1 or 2. It will choose the route for 1 because that is the lowest routing metric. Let's look at our routing table for RIP version 2 again. We have that one line in the routing table to 10.10.30.0/24. It has an administrative distance of 120 because it is RIP version 2, and it has a routing metric of 1. RIP uses the number of hops to a location as its routing metric, so we know that this particular destination is 1 hop away. To be able to reach that particular network, we would go to 10.10.50.2, and we would get to that particular location by sending this traffic out serial 0/3/1 on this router. If you were to use a different routing protocol, for example, EIGRP, you would have a very different routing metric. Here is the same routing table to the same location, but we've enabled EIGRP instead of RIP2. You can see this line in the routing table was created with the code D, and if we refer back to our legend, we can see that D does refer to EIGRP. Everything in this line is very similar to what we saw with RIP version 2, although you'll notice the administrative distance is different. It's a 90 because EIGRP has a higher priority in its administrative distance than RIP version 2. But you'll notice that the routing metric that is determined by EIGRP is very different than the routing metric that we saw for RIP version 2. RIP version 2 uses the number of hops, whereas EIGRP has a completely different calculation that it uses to determine what the best route might be. As you work more with routing tables and begin evaluating these routes on the fly, you'll become much more comfortable with determining where the best next hop might be for a particular packet. One of the challenges we have when working with routers is that there's only one best route to a different location. If you were to look at the IP configuration of your device, you'll notice that you have a default gateway. That default gateway is your local router that allows you to communicate outside of your local IP subnet. But you'll notice that there is only one IP address available to list as the default gateway. You can't list multiple gateways in that list. And this brings up a challenge, especially when you'd like to have redundant routers on a single network. One way to provide redundancy, even though you only have places for a single default gateway, is to create a virtual IP address for the router that's in use. We refer to this virtual IP as a VIP. And the idea is that if the primary router disappears, we can move that virtual IP to another router on the subnet so that you don't have to change everyone's workstation to maintain the uptime and availability of the network. This means you, as the end user, may have no idea how many different redundant routers might be on your local subnet. And if the primary router on your network was to fail and the virtual IP address was to move, you would seamlessly continue to have connectivity using that redundant router. Here's how this would work. You, as the end user, would communicate to a router or a default gateway on your network, and that default gateway gives you access to other subnets or allows you to communicate out to the internet. In this particular example, we're going to use the first hop redundancy protocol, or FHRP, in conjunction with a virtual IP address that we've associated with router 1. This is our active router. Also on the same subnet is a standby or backup router. That's our router 2. Our default gateway is going to be associated with the virtual IP address that we've got associated with router 1. And that means that all of our traffic will flow out of our network through router 1. If router 1 was to fail, there would need to be some type of method to fail over to router 2. But router 2 has a completely different IP address. In this configuration, router 1 and router 2 are always in communication with each other. But if router 2 suddenly realizes that it's not able to communicate with the active router, it then removes that as the active router and becomes the active router itself. Then it takes control of that virtual IP address so that everyone on the network is now able to communicate out to the internet through router 2 using that original virtual IP address. All of the traffic will flow just as it normally did, and the end user has no idea that it's now using a completely different router to be able to perform that communication. Another interesting characteristic of switches and routers is that you can assign multiple interfaces to a single physical interface. We refer to these as sub interfaces. So even though there might be a single Ethernet interface on a router, we can take that single Ethernet interface and separate it into multiple virtual interfaces. For example, we might have a trunk connection that has multiple IP subnets connecting to a single physical connection. But we may need to reference each individual VLAN in a trunk with a separate IP address on our router. We do that by assigning that physical interface with an additional parameter called a sub interface. So although the physical interface on that router is referred to as Ethernet 1/1, we would have separate sub interfaces within that physical interface that might be called Ethernet 1/1.10, Ethernet 1/1.20, and Ethernet 1/1.100. This means that we can set different configurations for each of these sub interfaces so that we can reference them with the appropriate IP address for that VLAN. Here's how this would look on a network configuration. You can see there are 3 devices. All 3 of these devices are in separate VLANs. There's the red VLAN, the green VLAN, and the blue VLAN. And of course, they're connecting to separate physical interfaces on a switch. The switch then has a single cable between the switch and the router, and it's trunking each individual VLAN within that single gigabit connection. On the router side, we've configured 3 sub interfaces for that Ethernet connection: sub interface G0/0.1, .2, and .3. And then we can assign IP addresses, subnet masks, and have completely different routing tables for each of these individual sub interfaces as if they were physical interfaces on that router.
Bien, mi gente, ya lo que nos quedaría es este último video. Déjeme revisar en efecto, ¿no? Que es el que nos queda, ¿verdad? Porque son sé que han sido varios videitos, exacto. Con este vamos a terminar, que es el NAT, lo que es el Network Address Translation, para entonces regresar al material del módulo y que veamos las dos tareas que tienen que entregar, ¿ok?
There are many devices connected to the internet. Some estimates are 20 to 30 billion. And by the time you watch this video, it's probably, of course, going to be more than that. One of the challenges, of course, is that IP version 4 only supports 4.29 billion addresses, and we have completely exhausted our list of IP version 4. There are no more addresses or subnets to be handed out. So now we have to find some way to communicate across the internet to these billions of devices using a protocol with a relatively few number of IP addresses. The way that we're able to make this work is through a technology known as network address translation, or NAT. We often refer to NAT as being the way that we are able to extend the functionality of IPv4 and use so many different IP addresses, but NAT can be used for many different use cases. We just in this video happen to be talking about one of the most popular use cases where we are able to translate IP version 4 from a private address to a public address. If you wanted to get more details on the difference between a private IP and a public IP, you'll want to look at RFC 1918, which defines these different ranges of private IP addresses. These are IP addresses that are not routable on the public internet. So we most often use these inside of our homes and inside of our businesses, and we'll perform translation if we ever need to communicate out to the internet. Certain ranges of these IP addresses are probably already familiar to you. For example, one IP address range that is private is 10.0.0.0 through 10.255.255.255. In a large enterprise network, this is probably the IP address range that you're using. This RFC also allocates 172.16.0.0 through 172.31.255.255. And if you're using network address translation at home, you're probably using the IP address range of 192.168.0.0 through 192.168.255.255. So how are we able to take these private addresses, which we already know we cannot route across the internet, and somehow we are able to communicate to these internet connected sites? We are able to do this using network address translation. Let's take this example where Vala would like to communicate to the Professor Messer web server. Vala's IP address is a private IP address of 10.10.20.50, and Vala wants to communicate to a public IP address of 104.20.19.63. To follow this process, let's break these two addresses out and identify them as the source IP address of 10.10.20.50 and the destination IP address of 104.20.19.63. This packet will first hit a router that is configured with network address translation. This router knows that the source IP address of 10.10.20.50 is an internal IP address, and we can't use this IP address if we want to communicate out to the internet. So this router will change or translate that address to something different. This router already has a list of IP addresses that could be used, and in this case, it's changed that IP address to 94.1.1.1. Now we have a public IP address, so now we can communicate directly to the Professor Messer web server. For this web server to communicate back to Vala, it's obviously not going to communicate back to the internal 10.10.20 address. Instead, it's going to reverse those IP addresses, and the source IP address now becomes 104.20.19.63, and the destination IP address is the 94.1.1.1 that was originally assigned by the network address translation router. When this router now receives that packet, it's going to perform the translation again, except in reverse, and modify that destination IP address to be the internal address of 10.10.20.50, which obviously matches the IP address of Vala. And now Vala has received that message from the Professor Messer website, even though Vala has an internal private IP address. With standard network address translation, we are translating from one IP address to a different IP address. This means that if we wanted to have many people performing this translation, we would need to have many more public IP addresses available. There's a way to make this much more efficient using a different form of network address translation called NAT overload or port address translation, or PAT. Let's take that same example where Vala would like to communicate to ProfessorMesser.com. Vala's IP address is 10.10.20.50, but you'll notice we'll also include the source port number, which in this case is 3233. The destination IP address is obviously the IP address of the Professor Messer web server at 104.20.19.63. And in this case, Vala is communicating to that server over port 80. When that packet is received by the router, it understands that 10.address needs to be translated to a public IP address. And inside of this router is a network address translation table that shows both the private address and the public address that it's translated to. You'll notice here that the private address of 10.10.20.50.3233 is converted to 94.1.1.1 with a port number of 1055. And when that translation takes place, our source IP address is now a public IP address, and that's what's received by ProfessorMesser.com. Because we're translating both the network address and the port number, other devices on this network could use the same public IP address. For example, let's take another scenario where we have Jonas at 10.10.20.70. Jonas's random port number that's used for this transaction is 5782. And of course, the destination IP address is the same as the ProfessorMesser.com web server with a port number of port 80. When that packet is received by the network address translation router, it knows that that address has not been used before, and it puts that into the network address translation table with a different port number on the public IP address side. So now we're using the same IP address of 94.1.1.1 as our public IP, but notice that the port number has incremented by 1. This means that we can now have many people on the inside of our network communicating externally to a server, all using the same public IP address.
Bien, ya terminamos con los videos. Vamos a regresar entonces al material correspondiente del módulo. Para este módulo, mi gente, solamente tenemos dos tareitas, que es, recuerden, tienen el foro de discusión. Gente, recuerden que los foros de discusión, aparte de usted realizar su aportación, es importante que usted le conteste, ¿verdad? O responda a la aportación de sus compañeros. Recuerden que los foros de discusión se crean con la finalidad de que ustedes puedan interactuar entre sí, máxime, ¿verdad? Cuando estamos en un curso que es completamente a distancia, que hay lo que se conoce como una distancia transaccional, ¿ok? Por lo tanto, es bien importante, ¿verdad? Que en esos foros de discusión ustedes participen, hagan su aportación inicial, por favor, eviten información de ChatGPT. Yo me di cuenta rápidamente cuando es información extraída de AI. He sido bastante benevolente en ese sentido, ¿verdad? Porque lo he dejado pasar. Pero recuerden, de nuevo, recuerden que la información de la inteligencia artificial no siempre es información confiable, no siempre es información fidedigna, no siempre contesta lo que se le pide. Es importante que ustedes consulten fuentes de información que sean siempre confiables, ¿ok? So que en este caso, a veces también me he dado cuenta que las referencias que colocan en los foros de discusión no existen. Así cuidado con eso, porque son referencias que le genera el ChatGPT, que supuestamente son enlaces que existen, pero realmente no existen, ¿ok? Bien, vamos a ver el primer laboratorio, que es instalar, de instalación de un router empresarial. Para estos fines, ¿verdad? Esto es una simulación, ¿verdad? Que ustedes tienen que completar en el test out. Pero aquí yo les puse un video tutorial, ¿verdad? Que les explica paso a paso, pues, cómo hacerlo. Aunque está en inglés, lo pueden hacer. Vamos a verlo.
Soundstripe. 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 stripe. Sound 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 stripe.
Hey, I'm Bob.
Ok, ya terminamos. Vieron ese primer laboratorio, un poquito trick, pero de nuevo, véanlo con calma para que lo puedan hacer y sacar una buena puntuación. Vamos ahora a ver el de Cisco Troubleshooting Tools, que es otro video que les coloqué aquí. Y nada, cualquier duda o pregunta, me dejan saber, ¿ok?
See this scratch?
Ok, mi gente, ya tenemos básicamente todos los laboratorios discutidos, inclusive hasta el que lo está explicando también tuvo un poco de problemas en las últimas dos preguntas, pero nada, gente, recuerden, ya estamos en cuarta semana, ya llegamos a la quinta. La quinta semana básicamente son el tema de resolución de problemas en la red, lo que es la parte del troubleshooting. Recuerden que el troubleshooting puede ser a nivel físico, a nivel lógico, a nivel de comando, a nivel de software, a nivel de hardware. Es una parte, ¿verdad?, que es muy importante también. Pero para eso, ¿verdad? Les recomiendo, ¿verdad? Para el módulo 5 para que comiencen su estudio, vayan al profesormesser.com, vayan a Network Plus y de nuevo le damos un clic aquí y él tiene básicamente en los últimos módulos, básicamente en la 5 sección 5 tienen todo lo que es el Network Troubleshooting. Gente, este es el mejor recurso que existe en formato de video para estudiar para este examen, es ese que está ahí, ¿ok? So que en ese sentido, mi gente, mi recomendación es que usted saque un poco de su tiempo, ¿verdad? E invierta en estudiar la sección 5 del profesor Messer para que puedan salir bien. En este sentido, ¿verdad? Mi recomendación, denle cariño a esta sección, particularmente a la sección 5.1, a la 5.2. Mira, la 5.2 tiene que ver, ¿verdad?, con problemáticos a nivel de capa 1, básicamente del modelo OSI, que son todo lo que son los elementos físicos, como los cables, las interfaces, o problemas a nivel de hardware. Ya, mira, ahí tenemos a nivel de servicios de red, problemas a nivel de capa 2 y capa 3 del modelo OSI, problemas a nivel de switching, switching es capa 2 del modelo OSI, capa 3, routing, problemas con direcciones IP, problemas de rendimiento. También nos podemos encontrar con problemas de rendimiento, que el internet está exageradamente lento, me tardo muchísimo en conectar a la impresora, el tiempo de respuesta es bien lento, la latencia está muy alta. Tenemos herramientas y protocolos, ¿verdad? Que es la última parte, como por ejemplo herramientas de software, herramientas de línea de comandos, herramientas de hardware y algunos comandos básicos de redes, que son importantes que ustedes los conozcan con el fin de obtener información de configuración y no tan solo eso, que también podemos hacer en este caso lo que es la parte del troubleshooting. ¿Ok? Estamos. Cualquier duda o pregunta, siempre estamos a la mejor disposición para poderles aclarar. Recuerden, mi gente, ya estamos en cuarta semana. Se supone que hoy hagan la entrega de las tareas del módulo 4 y ya en esta última semana, pues, hacer la entrega de las tareas del módulo 5. ¿Ok? Cualquier duda, pregunta, comentario, inquietud, sugerencia, estamos a la disposición de poderles ayudar. ¿Ok? Bueno, de nuevo, ya terminamos el módulo 4. Gente, cualquier duda o pregunta, estamos disponibles, ¿verdad? En caso de que hiciera falta, ¿ok? ¿Estamos? Bien. Voy a tumbar la cámara. Ya, buenas tardes, mi gente. Ya, pues básicamente contesté los mensajes pendientes. Dudas, preguntas o comentarios, estamos siempre a su orden. Bendiciones y excelente fin de semana y felicidades a los que son padres aquí. Linda tarde.